So in many respects, that's a kind of old story. So, but somehow I just, at least to me, figured out recently how to push through some details. So I'm going to start from something in kind of general level. So the picture is kind of like this. So you've got some base space, so maybe two-dimensional, but at this stage it doesn't really matter. So you've got some smooth space M, and then you're going to look at different metrics on this space. So same space, and then you're going to start changing the metric. So maybe you've got some like orthogonal metric that gives you some grid on the original metric, and then you've got a new metric, and the orthonormal grid is now deformed. And now on each of these guys, you're going to put some random structure. So you've got maybe some okay, so like we had, for instance, in Remy's talk, you can think of having some action, some abstract action on some field. And now this action has to be somehow consistent across metrics. So for each metric, you've got an action, but it's not really one fixed action on one fixed metric. You should think of having the collection of actions. So your model is not just a fixed space. So you should think of having a consistent model across spaces. And now, given such a model on a fixed space, you can start looking at correlations. So which I'm going to denote like this. So maybe your basic field is phi, so maybe you're just going to look at the correlations of phi. So you can even think of phi as being a free field or something like that. So you're computing some correlator with respect to your action on your original metric. And then you start changing the metric, and the points stay at the same place, and because you have this consistent family of actions, you can look at this correlator at the same time for all metrics. Okay, so now what you're going to start looking at is okay, so maybe I can, give indices to these fields. So what happens when you start varying the metric? And specifically, you can think of having a local variation of the metric, which is away from your insertions. So the z's are fixed. The metric near the z's is fixed, and you start changing the metric somewhere else. Okay, and then you try to write a basically Fréchet derivative of this quantity. So you're going to take a derivative of this with respect to this variation. So you take this Fréchet derivative, and if, for instance, my metric stays fixed near my insertion, and I start deforming this metric somewhere else, then effectively what I'm going to have is something which is going to be a linear form, which is going to operate on correlators. And something which operates on correlators, you can think of being some abstract field. So you can write this as your basic correlator. I'm going to write. Okay, so we're going to represent so you have this widget which actually represents this operation of deforming the metric in a certain way at a certain point. Okay, and then if everything is nice, I mean, you can actually define this. Okay, so now if you have a conformal field theory, actually this guy should not depend on G, but just on the metric, on the conformal structure which is defined by G. So now I'm going to go back to 2 dimensions specifically. So in CFT, actually, what's going to matter is not the variation of the metric, but the variation of the conformal structure in first approximation. So we're going to have the same picture, but now we're just going to vary complex structures. So I'm going to have these consistent families of actions across complex structures. I'm going to fix my insertion somewhere, and I'm going to make a local deformation of my complex structure at some point. So now specifically how is it working? So I've got my original now Riemann surface with some given complex structure. So these grids are basically straight angles for my complex structure. I mean right angles for my complex structure. And then a classical way to think of local deformation near some point Z is going to go as follows. So I'm starting from this surface. I've got some disk around Z, and I'm going to pull out this disk. Yes, I'm going first step. I'm going to pull out this disk. And now my surface consists of the outside, which is there, the inside, which is there, and I've got some identifications. So points on this annulus are identified in that annulus. Okay, now what you're going to deform is, so the trick is to deform the identification. So in general, complex manifolds, so that goes back to Kodara and Spacer. So you're going to start deforming these identifications. So that guy now is going to be slightly deformed. This guy is going to, this identification is going to change a bit also, and so on. So I've got this new identification. So the points stay the same. The identification between these two things is new. So you go back to very basic thing as saying what's a Riemann surface? It's an atlas of disks which are identified. And you keep the same atlas, the same disk, and you change the identification. So that's your deformation. So now if I'm just going to look in front at this annulus, so the point which was identified just vertically, straight, if I'm looking from the right, is going to move a bit. So my deformation is effectively an holomorphic vector field in the annulus. So if I choose a local coordinate little z, so that this annulus, so that's an annulus in C, now because I choose a local coordinate little z, and anything which is holomorphic in an n-unius I can write as a Laurent series. So it's sum of an, zn, let me put like zn plus 1 already, d over dz. Okay, so that's it. So in particular, okay, so I've got a sort of natural basis for this. So I'm not really going to care about convergence, but I'm just going to fix one mode. So if I'm looking at this element, what's the upshot? So if I choose a manifold, I choose a point, I choose a local coordinate, and I choose an integer, I've got this first order deformation of my complex structure. Okay, so again. So if I specify this data, a geometric point, a choice of local coordinate, and a choice of vector field in that coordinate, then I'm going to define a tangent vector to the space of all complex structure, which is a moduli space. Okay, so now now we want to move to vector fields. Okay, so if I fix little n, let's say -2 or something like that, I can try to do this operation for all surfaces. So any surface which has a marked point and a marked local coordinate at this point, I'm going to get a tangent vector, a first order deformation of this surface. So for any surface, I've got a first order deformation, so effectively I'm getting a vector field on the space of complex structure. So now the issue is that you need to keep track of additional data to define that guy. So the mark point is fine, right? But then you need to keep track of a local coordinate, and then you start getting into a bit of difficulty. Okay, so I'm starting from a surface sigma on which I've got a marking consisting of a geometric point big Z, so capital letter for geometric points, small letters for local coordinates. So given a point and a local coordinate little z, I've got this first order deformation. So n is fixed. So now simple observation is that you don't need the full local coordinate to define your deformation. Why so? Because when n is in this picture, when n is strictly positive, you're not actually doing anything to the complex structure. So when n is strictly positive, this vector field extends holomorphically to the inside. So what you're doing is just changing the analytic coordinate. So the complex structure is fixed, and what you're changing is the analytic coordinate. And specifically, if you work out what's going on, what's going to happen is that you're going to replace your analytic coordinate by a deformation of this analytic coordinate, which is z minus the small variation delta times z to the n plus 1. So if you work this out, so what's going to happen is that in order to evaluate this deformation at the level of the complex structure, you don't need a full analytic coordinate. You just need a large enough expansion of your analytic coordinate. Because if you have two analytic coordinates, which are equal up to large enough order. If you look at this vector field minus z n plus 1 d over dz written in both coordinates, they are going to be equal up to an holomorphic vector field. And holomorphic vector fields are inert on the complex structure. So you don't need a full analytic coordinate, you just need a large enough number of coefficients to your analytic coordinate. So in order to evaluate this deformation, you just need z modulo something which is a multiple of z to some large power. So now we're almost there. So yes, I'm going to define a first space, which is, so I'm going to fix some type of Riemann surface. I'm going to have at least one point at which I'm going to do the deformations, which I'm going to call z. I can keep track of any sort of additional markings. And among all surfaces of this type, I'm going to quotient by conformal equivalence. So conformal equivalence, which preserves the complex structure on all the markings. So that gives me a nice space, which I'm going to call T0. So that's a nice finite dimensional analytic space by general Teichmüller theory. So if you put enough markings. And then I'm going to start moving up. So I'm going to define a new type of surface with additional information, which is all the information I had before plus a one jet of local coordinate at z. So meaning that two local coordinates are considered to be equivalent if their derivative is 1 with respect to the other. So I've got more information there. So this guy is going to be another nice analytic space, which is going to cover the other guy. And then I can go on
examples? I mean, the dimension of this guy is, for instance, the sphere, there's only one control structure.
Yeah, so the sphere you need to, well, I mean, you know, it's all right. So when you look at dimension of moduli spaces, you've got to subtract the dimension of the automorphism group.
Yeah.
And that's annoying. So I mean, you just put enough markings so that you're going to kill all the automorphisms, in which case you're going to go up by 1 each time. So dimension is going to go up by 1 as soon as you put enough marking to kill all the automorphisms at the basis.
So what's the dimension for the sphere?
So sphere, it depends on your number of markings. So if you have if you have 1 plus 2 points, which is kind of minimal, then you have 0, so that's just a point. And then you're going to start adding stuff. But then you could have over mark points. And then if you have 1 mark point, then you have just the space of cross ratios. So you have a line of possible cross ratios of your 4 points. And then you're going to start adding stuff. Okay, so you have just this tower of analytic spaces. So the point is that if you want to compute this deformation at some level, you need information at a higher level. Because if I want, for instance, to compute a deformation of type L-2 on this surface, so its action at this level, I need to use a local coordinate which is precise enough. So I need to move at some higher level. So the upshot is that these vector fields are well defined on this, if you take basically the projective limit of such analytic spaces. We take the projective limit of this sequence of spaces, so meaning 1 point is this projective limit is just a sequence of points which is consistent under projections. Okay, and then you want to define a basically vector field on this. So this is each of these guys is a very nice space. So each of these is a finite dimensional analytic space. All the covers are analytic and so on. So you don't need to get into technicality, so you can just define you can define a notion of smooth function in the very cheap way. So you say that on this space, anything which is smooth is something which depends on finitely many coordinates in a small neighborhood. And once you depend on finitely many coordinates, you're on a regular analytic manifold. So you have a notion of smoothness, which is just a very weak projective limit of smooth functions. So anything which is smooth on one of these guys is smooth on the projective limit, and vice versa, anything which is locally smooth in finitely many coordinates is smooth. And now you can now perform this at this level, so now you can define differential operators on these smooth functions. So these guys are derivations, so first order differential operators. So what's the operation? So for a little l sub n, so little l sub n, so you take 1 point there. You look far enough to get a large enough jet. Once you have a good enough approximation of the local coordinate, you do this local deformation. So you pull out a disk, twist it in this local coordinate. You read off what happens to your function when you do this, and you take the derivative, and what you get is a differential operator on that space. Okay, so then it's pretty cheap to check that you have this commutation relation. So these are first order differential operators. So you can take brackets. Bracket is another operator of the same type, and then you can check that you get this relation. So this relation holds as operators on this big space of test functions. And this is actually, I mean, this follows from the same so we started from basic vector fields, holomorphic vector fields. These vector fields have trivial commutation relations, which you can compute directly, and you just need to follow that. Basically, this translates to that. So I mean, you take a disk, you pull it out, you twist, and then you take a smaller disk, you pull it out, you twist. A smaller disk, you untwist, an even smaller disk, you untwist. That's one commutator, and then you work out that. That's exactly what you get. Okay, so at this stage, so all of this is very classical. So at this stage, you get a realization of these operators on that space. Okay, so now we are going to get into a non-zero central charge. So somehow we started by saying that, you know, in CFT you don't care about the metric, you just care about the complex structure, but it's not, of course, quite true. So somehow you sort of remember that at some point there was an actual metric, and then you're not going to lose all the information. You're going to get some remnant of the metric. So maybe, yeah, I don't have that much time, so I'm going to so I'm going to fix some surface sigma. I'm going to look at some reference metric G. I'm going to look at all metrics which are conformal to G. So I'm going to look at all the Riemannian metrics which correspond to the same complex structure. So I'm going to ask, you know, what's a nice functional on the space of all these metrics. So the kind of thing you're shooting for is some regularization of the partition function of a nice model, which the regularization is going to depend on the metric. Okay, I'm going now to fix the metric and just vary according to the within a conformal class. So G basic matrix is fixed, sigma is going to vary, and I'm going to ask, you know, a priori it's a huge space, so functionals of all this space of metrics. So that's a huge space. So among all these possible functionals, which are kind of reasonable ones, so you can argue in the following way. So you can argue that you're going to try to compute Frechet derivatives. So I'm going to fix G. I'm going to try to start computing a Frechet derivative of f in direction G. In direction sigma. Okay, and this Frechet derivative should be a linear form in sigma. Sigma is a function on my surface. So a linear form on functions of my surface is just integrating sigma against some two forms. Okay, so now I'm going to ask what are the reasonable, you know. So this is effectively the gradient of f. Okay, so that's effectively a gradient. So now, what are the nice two forms on my surface? I'm looking for a two form which I can express intrinsically in terms of the metric. And actually, there are very few of those. So there's just okay, so it's a basically classification result in Riemannian geometry. Given an abstract Riemannian surface, what are the two forms you can fabricate just from the metric? Okay. You have certainly the volume form in 2 dimensions, and then you have also the curvature form. So if I pick the volume form, what's going to be my functional? Well, the functional is just going to be the volume. So it's it's a reasonable functional, but not one I terribly care about. And now, if you pick the curvature, then you're going to get something which is much more interesting. What you're going to get is something. You're going to get a conformal anomaly. So now I'm going to fix omega to be the curvature.
Why did you say it would have this form necessarily?
I'm looking at the nice guys. So the nice guys which I can express completely intrinsically. So of course, in principle, I could have a mapping which takes an abstract surface and computes a two form on this surface, looking at the global data, etc. But I'm looking at something which is going to be completely local. So this can be computed locally from the metric. So these two forms at a point can be evaluated from the metric at this point. So what I was saying is that precisely this. So there's this result telling you that what are the metrics you can compute locally in terms of the metric tensor and its derivative. Okay, in this case, which is quite low dimensional and simple, that's what you get. And then, so that's an ansatz. So I'm looking at this gradient, which is local. And the coefficient in front is fixed. Okay, so when I vary the metric, I'm looking at a fixed coefficient. So I'm making basically an ansatz, but it's not a complete, I'm just arguing, but it's not a crazy, it doesn't come out of the book. So I'm going to try to get a functional whose derivative with this gradient is given by sigma, which I evaluate against the curvature tensor. And then that guy integrates to, so actually that's something you can integrate. So I'm going to get, so I'm going to apply this thing, and I'm going to get something like this. Something like that. Okay, again, kind of familiar from what we saw in Remy's talk. So that gives you a Liouville cocycle. So yeah, so basically you integrate from 0 to 1 this using that formula, and that's exactly what you get. So this comes from this basic ansatz, but looking at functions of the metric, which have some canonical local variation. Okay, so now we are going to look at the following. So yes, I'm going to explain that. So again, what we're kind of trying to shoot for is some sort of regularization of partition functions of reasonable models. So basically, if I exponentiate picture I had before, I'm looking for some functional of the metric, which within conformal classes is going to vary in this simple way, so that if I change from G to another metric in the same conformal class, I'm going to pick exponential of some fixed multiple, little c, which is the central charge of that uveal cocycle. So now, it's a point which I guess I don't really have time to discuss if I want to go anywhere near SLE, is that so you can, what we had before is an action of so the action we had before was an action on functions which depended only on the conformal structure. So if you have c is equal to 0, you get something which depends only on the conformal structure. So this action tells you how you vary within a conformal class. And then you need to see how you vary across conformal classes. So that's completely not covered by this thing. Okay, so what we explained before was an action telling us that functionals of such type with c equal to 0, we had some action of the little ln's. And I'm going to so I'm going to look at test functions which depend on now more data. So I'm going to get a surface, a mark point, a sufficiently good approximation of a local coordinate, whatever markings I feel like keeping track of, and a metric. The dependence on the metric is going to be very simple, given that if I know the value for any metric in the conformal class, I can compute the functional across all other metrics in the same conformal class by this formula. So effectively, if I choose a slice of metrics, one metric for each conformal class, I've got effectively, again, a functional which is of the same type as what I had before. But now, because of this, you're going to get some twist to your action. So, I mean, there's a way to basically canonically move to extend the picture I had before within that. Within such a family, and what you're going to get is now okay, so again, these are basically differential operators on these classes of functions which satisfy what they should. Now you get a correction to the commutation relations we had before, and this correction is given by the central charge, which is the one you read off in this conformal anomaly formula. So what you get is a representation of the Virasoro algebra operating on this big space of functionals. So on that class of functions. So I want to insist that this representation is completely local. So I mean, all the computation of deformations are done locally. Okay, so maybe just to Okay, so just to kind of like elucidate the nature of this construction. So you can look at a simply connected domain, so you can uniformize so that your simply connected domain is H, and I'm going to keep track of a certain number of points, so 1 point, when I'm doing the deformation on any number of mark points. Okay, so I can fix 3 of my mark points to be 0, 1 on infinity, so that I'm just killing automorphisms. So I've got a point Z where I'm going to do the deformation. I've got some points I'm keeping track of. Okay, so my coordinates on this space, so coordinates. Okay, so maybe I subtract. Okay, so I need to specify where these points are once I uniformize. So I've got okay, so n minus 3 coordinates for my mark points plus 1 coordinate for my deformation point, and then I need to keep track of a jet of local coordinate at this. Because I'm in H, this is just some analytic function in H. I'm just going to look at the Taylor polynomial of this analytic function up to some large n of order. So my coordinates are position of these points plus coefficients of some Taylor polynomial. Okay, and each of my differential operator is going to be a differential operator in finitely many of these coordinates. So the z's, the x's, and the a's. Okay, so you've got a first order part, so you've got d over dz times some smooth function. So what's a smooth function? It's just a smooth function of finitely many of these coordinates. And then your guy, okay, so technically your guy goes forever, but if you apply it to a smooth function depends only on finitely many coordinates by definition. So it's going to truncate. So you just, you have this infinite list of coefficients which you need if you try to apply ln to a function which depends on a lot of the s. And then, so this is a first order part, and then you got a potential, so C is some now constant times some potential, which is some function of your actually s, which you can basically compute from the Schwarzian derivative of one guy. And now these operators satisfy this commutation ratio. So you construct a fairly explicit, so for each choice of type, so in this case I started by basically the simplest type, which is simply connected domains with some mark points. You have these differential operators operating on this type of functionals. Yes, so maybe I somehow over-ambitiously I put that in my tether, so now in whatever is left I'm going to to start trying to show how this connects to SLE. So up to now, I mean, it's a kind of nice construction which is largely classical, starting from Bayesian, Shechtman, and Kontsevich in particular. So now, at some point, you can connect with SLE. So you have this operation on functionals of some, conformal types on the one hand. On the other hand, you can think of a special type of functionals which you care about, which are correlators of some CFTs. And now you want to see how these guys operate on correlators of reasonable CFTs. Okay, so SLE. I'm just going to discuss localization for SLE. So the key, or basically the only ingredient in this part of the story is the result by Lawler, Schramm, and Werner on restriction of SLE. Picture it like this. Okay, so I've got a big domain D1, which is this square, which has 2 mark points. I've got a smaller domain D2. I've got 2 marked boundary points. So if I'm looking at the phase where kappa is less than 4, I'm going to look at some SLE in D1 going from A to B. With positive probability, this SLE is going to stay contained in that channel, D2. But I can also look at SLE in D2. Okay. So that's a probability measure on paths. I'm using Lawler's convention to use sharps for probability measures, whose mass is 1. So now the crucial result is the following. Okay, so crucial result is the following. So if you look at paths in D1 of SL in D1 and you restrict SL in D1 to paths which happen to stay in D2, this gives you a probability measure on paths in D2 from A to B. This probability measure is absolutely continuous with your original probability measure, and its Radon-Nikodym derivative is some explicit functional, which is about as explicit as it gets, given that it's a functional depending on a domain, a subdomain, and a path. So given a domain, a subdomain, and a path, you compute a number, and that's actually pretty nice given. So now there's an observation which is essentially due to Kontsevich and Suhoff, which is that you can unpack this density. Okay, let me write it like this. Okay. Okay, so if you apply restriction twice to D1, D2, and D3, where D3 is even smaller, it's clear that FD1, D2 times FD2, D3 is equal to FD1, D3. So in particular, it tells you that Okay, so that's a kind of co-cycle in the sequence of domains, and you ask whether it's a co-boundary, so whether you can find functions g of the domain on gamma, such that this f d1, d2 of gamma is some g d2 of gamma divided by g of d1 of gamma, which is consistent by taking restriction iterated. So now the trick is that except when kappa is equal to 1/3, in which case that's the original restriction for statement, this is constant. So except in the case of zero central charge, you can do this, but you need to extend your data. So on the left-hand side, everything depends only on the conformal type of your picture. But if you want to unpack this co-cycle into this co-boundary, you need to add data to your guys. So you need to put matrix on this. So you can do that if you extend some data. So, in the left-hand side, you don't have a metric dependence, just a conformal dependence. On the right-hand side, you've got some metric dependence on each side, which is going to cancel out. But somehow you need to put it back. So you can do this. And once you've done this, then it's going to be very cheap because you can write simply that. Okay, so of course I did it in the reverse direction. So. Okay, so now I can multiply these two measures by the g. So the g's are of course not unique because, for instance, I could just multiply by some multiplicative constant. So if I pick some of the g's, I can rewrite this restriction property like that. And now this tells me that this measure g d mu star is going to patch in the following sense. You didn't start with, yeah, okay. So, now if you look at something which looks a priori complicated, which is to define SLE on some more complicated geometries, well, I mean, okay, so you got to try to define these probability measures on paths. So again, I'm just looking at kappa less than 4, so simple paths going from A to B. So it's some probability measure on path space, but then path space, what's path space? So if you have just one path, given any such path from A to B, you can find a tube around this path. Okay, so you can find a tube around this path. So the space of all paths is covered by some small open subsets. So for each tube going from A to B, you're going to look at paths staying in this tube. So that's the union over all tubes of these events. And now if you fix a tube, well, now a tube is simply connected. So now if you want to define your law on your path space, you can just restrict it to each tube. On each tube, you just need to define a law on paths in simply connected domains, in which case you can start from there. And you need it to do consistently. And to do it consistently, you need to patch what happens in different tubes. And what tells you that you can patch what happens in different tubes is exactly this. So if in each tube D So you're going to use as reference measure SLE. You're going to put a factor which is this G. You have this consistency condition on the G's, which is that G d1 divided by d2 has to be this fixed explicit functional coming from chordal restriction. If you can solve this relation on top, then automatically you're going to define a measure on top space. So that also goes back to Kontsevich and Suov. Okay, so on the one hand it's very cheap. On the other hand, you got to pay a price somewhere. So for instance, it's not clear that what you get is a finite measure. So it's just like a locally finite measure. Okay, so let mu sigma to be this measure which I'm going to obtain by patching. So this is a fairly abstract thing, and I'm going to look at its total mass. And now this total mass is a functional on my surface. Okay, and what does it depend on? It depends on a few things. So in particular, when I say that in order to unpack this restriction cocycle, I need to put the metric back in. So that guy is going to depend on the metric, and its dependence on the metric is going to be via the conformal anomaly formula. So this is going to be one of these nice functionals with a nice dependence on the metric. So at least when central charge is negative, and in some other cases, you can actually check that that guy is actually finite, which is not clear from the construction, by just lifting everything to the universal cover and comparing to what you have on top. And on top, you can compare with SLE on the universal cover. This is going to work if inequalities are in the right direction, which is when C is non-positive. Okay, so another point is that, even regularity is tricky. From the definition, even from that definition, it takes work to show that that guy is just measurable in terms of the underlying metric. Because this is for a fixed surface. You've got this construction for a fixed surface, you construct a measure, you compute its mass. It's not clear what happens when you change your surface. Yeah, so I'm almost done. So okay, so one basic lamp, so somehow it takes like 60 pages to get to that equation, is that given that you define this basically in a sense partition function from SLE from this patching thing, so now you define the functional on this space of metrics on the one hand. On the other hand, you have this general geometric operation making constructing a Virasoro action on functionals with the same conformal anomaly. And then what you check is this so-called singular or null vector equation, that this particular functional satisfies a particular relation, which is this. So L minus 2 minus 4 over kappa L minus 1 square. So that's a second order hyperelliptic differential operator on your space of functional of z is equal to 0. Okay, so obviously I don't have time, but so then just in exactly 1 minute. So the idea is that once you have this, you can start looking at fusion, which was basically main motivation for this work. So if you have multiple SLE paths, then again by these very cheap arguments, you can construct these systems of multiple SLE paths, and you get correlators from these multiple SLE paths, which are some abstract functional, which you may or may not be able to compute. And now, okay, so I should have specified that this deformation is relative to the root of the SLE. So the root is where you do the deformation. So when you have multiple SLEs, you have multiple deformations. So on the same SLE correlator, you've got this equation is going to be satisfied at each SLE insertion. So you have multiple differential equations. And then the game is to make this fusion of basically representation, where you have this Z depending on A, B, C, D, for instance, which satisfies one singular vector equation for the deformation at A, another singular vector equation for the deformation at C, is actually, when you're going to merge A and C, is going to satisfy the higher order differential equation. Okay, so, and again, in just one sentence, so the thing is that even if you're just looking at these correlators, which are just functions of the cross ratio, in order to work out this fusion, basically, you're more or less forced to go up to this level of infinite dimensional setup, where you have a full-fledged pair of commuting Virasoro representation to be able to work out the fusion, even though what you're really looking at the end is finite dimensional. So you need to go back to infinite, lift everything in infinite dimension where you've got full-fledged representations, and then go back down to finite dimensional setup. Okay, so yeah, clearly that was too much for. So thanks for your patience at least. Yeah.
So when you do this, do you see all of these higher dimensions for the virtual intersection?
So yeah, so you see, I mean, what you see very clearly is the border. So you see, so in the CAC table, you see very clearly all the border of the CAC table. What's inside is less clear. I mean, so the thing is that there are analytic steps. Analytic steps are good when the exponent goes up. So in the fusion, when the exponent goes up. So basically, you can do all fusions where the exponent goes up. So then you can move just on the top, if you will, on the bottom and right border of the CAC table. But then not, well, I mean, inside, you know, there are many of the steps go through inside, but not all of the steps. I mean, there are some like analytic steps which are actually quite painful to get everything to work. Yeah. But I mean, you could write, you know, what you think is in terms of SLE, you know, what is 2-2 in terms of SLE, it's pretty clear. I mean, you have a pair of dual commuting SLEs that you merge. But working out, you know, all the analytic details is not so clear because, I mean, in fusions, I mean, you need to, when you have like two possible fusions, you need to separate them. So when you have logarithmic singularities, so they're like expert on this, or when the exponent goes in, you know, in the wrong way, I mean, you have like a subleading series, then, I mean, there are additional difficulties which are not written yet. But you get all the Benoit Saint-Aubin formulae you get for SLE. Yeah.
Yeah, so you're always perturbing here on the boundary.
Yeah.
Right?
Yeah.
So if you want to do something with loops, compact, I think so.
Yeah.
A way to do something. Or
It's not really, well, I mean, so this thing is, okay, so maybe I should have said, so this equation is going to reflect the Markov property of SLE. So you cover your path space by tubes. In each tube, you have a reference measure, which is Cordell SLE, which has a Markov property. And when you basically work backward from this Markov property, there's a relation which comes out. So this expresses the Markov property of SLE in these patches. Okay, so you can certainly construct this. I mean, this Virasoro uniformization argument is actually usually done in the bulk. I mean, typically it's done on compact surfaces because it's algebraic, and actually everything is completely algebraic on compact surfaces. But then you don't get this kind of, you know, you don't get this kind of, well, I mean, you can write the representation, but then you, okay, I mean, it's not what you want to do with. But I mean, there are other things you can do, but not. I mean, singular vectors. It's not, you know, singular vectors in the bulk. It's not so clear what you would, you know, represent them in terms of SLE type objects. Yeah.
Other questions? Okay, so let's thank him again. Thank you.